In this video, I'm going to talk about one of the key issues of parallel programming. What happens when multiple processors need to access the same piece of data? This challenge exists because of the way computer hardware is designed. Any type of computer processor runs in a series of instruction cycles, where each cycle consists of fetching an instruction, decoding it, and then executing it. In modern computers, these cycles generally take less than a nanosecond, and clock speed is measured in gigahertz, or billions of cycles per second. However, as long as the number of cycles is finite, there is a chance that two cores will both send read or write requests to a memory location on the exact same cycle. So what should happen in this situation? The simplest solution is just to disallow this behavior entirely. Some memory systems are set up to be exclusive read, exclusive write, or EREW. This means that only one processor can access a given memory location at a single time. If multiple processors attempt to do so, then only one will be able to access the location. Depending on the implementation of the parallel system, the other processors may either be put into a queue or denied access entirely. This is one of the safest setups possible, but it obviously is slower than structures which allow multiple processors to read and/or write at the same time. When you think about it though, in many cases it doesn't matter whether multiple processors are reading the same memory location at a given time. As long as the value isn't changing, you'll get the same result. This is known as the Concurrent Read Exclusive Write System, or CREW. In this structure, any processors can freely read a memory location, but when a processor writes to the location, it essentially places a lock on that value, preventing any other processors from writing to or reading from that data until it has been rewritten. This mimics the way a lot of version control systems work for collaborative coding. One person checks out the code, makes changes, and then resubmits it, allowing others to check it out. The final and fastest method of handling conflicts is known as concurrent read, concurrent write, or CRCW. In this structure, there are no restrictions on accessing or editing memory locations. Any number of cores can simultaneously read or write to a single location. Obviously, this limits the number of wasted cycles, but it leads to a certain amount of ambiguity. What happens when two processors try to write different values to the same memory location in a single cycle? If a processor reads a memory location as it is being written, what value does it get, the old one or the new one? There are many different algorithms that can answer these questions, from picking a processor at random to weighting certain processors by priority, but it's important to know what is going to happen when such conflicts occur. It's important to keep in mind these three access types when designing your servlet. Unlike with conventional programs, it is often possible to know ahead of time where and how your servlet will be run, so you can design it specifically for that machine. For instance, a parallel-capable servlet created for an EREW machine should attempt to space out its reads as much as possible to reduce the probability of conflicts, while a servlet on a CREW machine can execute all of its reads at the same time. Although these three principles were designed specifically for processors accessing memory locations, the philosophies behind them are very important for the topic of the next video, dealing with parallel requests to your servlet.